we are discussing the finite fields and their applications, and mainly how we can construct a finite field. So, today we will continue that lecture on that polynomial arithmetic, as we have read the last lecture, that polynomial addition, subtraction, multiplication, and then finally how again we are able to do the polynomial division. So, once we can do the polynomial division, that means multiplicative inverse exists over ZP. Today we will see that modular polynomial arithmetic, how they govern to make or to construct some field. So, first we will read the modular polynomial arithmetic. So, if we remember that the example we have done, that first we have taken the field we have done Z8, and we have seen that is not a, actually that is not a field, if whenever the all properties we have studied. But if we do the operation on modulo 7, it becomes a field, and we concluded that actually the if we take the field is ZP P, where P is a prime, and the modular arithmetic operations are modular addition and multiplication. Now, if ZP is a ZP forms a field under modular addition and multiplication, then ZP to the power n also forms a field. Here P is prime and n is some integer, n is positive integer. Now, if we remember that whenever we have done the Z8, that we have studied the properties, we have seen that Z8 does not form a field. It is a ring, but since multiplicative inverse does not exist for all elements of Z8, whereas Z7, that means P equal to 7, forms a field. Now, 8 is 2 to the power 3. So, it is of P to the power n form, where P equal to 2 and n equal to 3. So, just now we have seen that, or we just mentioned that Z8 is not a, we have earlier read that thing also, Z8 does not form a field, but now we are doing that comments we are making, that Z2 to the power 3, how this becomes a Z2 to the power 3 becomes a field, and for that we will do the polynomial arithmetic or modular polynomial arithmetic. So, this is our intention of this lecture. Now, first we will see that we consider a set of polynomials, a set S of all polynomials of degree less than equal to n minus 1. So, we can write the polynomials, we write f x equal to a n minus 1 x n minus 1, since highest degree is n minus 1, x n minus 2 plus a 1 x plus a 0, and we can write I equal to 0 to n minus 1 a I x to the power I. Now, we consider the coefficients, that is the value of I, it is a I, this belongs to some z p. That means, we know we have defined z p is 0 to p minus 1. So, the total number of polynomials in the set is p to the power n. Since a can take p to the power n number of values, because each ai can take p number of values, ai can take p number of values, that is 0, 1, 2 to p minus 1, because as we wrote that ai belongs to zp and zp is 0 to p minus 1. And see, I have n number of coefficients a 0 to n minus 1, and so if I consider as it places, so we have n number of is. So, the total number of terms in the polynomial or all possible terms that will give one polynomial. So, all possible terms will be p to the power n. So, there will be p to the power n number of polynomials in the set. Now, we take some example. We consider that p equal to 3, for example, one we consider p equal to 3 and n equal to 2. So, p to the power n is 3 square, that means 9 polynomials are there in the set S. So, if we consider the polynomial variable, normally we call the indeterminate if is x, if the polynomial variable, that is the indeterminate is X, it is then what are the polynomials? Then these 9 polynomials, are as follows. See, n equal to 2, that means my AI can be only 0 and 1. P equal to P equal to 3. So, AI belongs to ZP and ZP is 0, 1, 2. So, AI can take value 0, 1, 2 and n equal to 2. So, the degree of polynomial will be n minus 1 . Polynomial is 1, that means a1 x to the power 1 plus a0. So, and this a0 a1 can take value from 0, 1, 2. So, if I take a1 equal to 0, if a1 equal to 0, then the first term will be 0 and a0 can be 0, 1, 2. So, the polynomial, the 3 polynomials we get, the polynomials 0, 1, 2. Now, if I get a1 equal to 1, because a1 can take. So, for a1 equal to 1, we get the polynomials x, because 1 into x, x. So, x plus 0 x. So, I get x plus 0, x plus 1, x plus 2. Now, a1 equal to 2, the polynomials are 2x plus 0, 2x plus 1 and 2x plus 2. So, these are my 9 polynomials. So, these 3 square, because p to the power n. So, these 9 polynomials, when for p to the power n, I write p equal to 3, n equal to 2. So, are 0, 1, 2, then x, x plus 1, x plus 2, then 2x plus 1, 2x, 2x plus 1 and 2x plus 2. So, these are my 9 polynomials. Now, if we consider another example, we consider another example 2, where we write p equal to 2 and n equal to 3. So, that since p to the power n, so is 2 to the power 3, that is there will be 8 polynomials in the set S. And what are those polynomials? similarly, if I consider the indeterminate as x, so here p equal to 2. So, p equal to 2, that is ZP will be only 0 and 1, because it is 0 to p minus 1, and n equal to 3. So, the degree of polynomial, so the polynomial, if I write f x equal to, it will be a2 x square, because n minus 1 is 2, n equal to 3. So, n minus 1 equal to 2, that should be my maximum degree of the polynomial, then a1x plus a0. So, this time there will be 3. Now, we take, if we consider a2, if a2 equal to, now I have to take all possibilities of a2, a1, a0. So, I can write a2 equal to, a1 equal to, a2 equal to 0 and a1 equal to 0, a2 equal to 0, a1 equal to 0, then a0 can be 0 or 1, a0 equal to 0, a2 equal to 0, a1 equal to 0, then a0 equal to 1. So, the polynomial is here f x equal to 0, here f x equal to 1. Now, I consider a2 equal to 0, but a1 is 1, because they can take 0 or 1 values. So, if a1 equal to 1, then if a0 equal to 0, then f x equal to x. If a2 equal to 0, that means all possibilities we are taking, a1 equal to 1 and a0 equal to 1, then f x equal to x plus 1. So, now for we have taken a2 equal to 0, all these values. So, now for same thing we can do for a2 equal to 1. So, this is actually for we have done a2 equal to 0 for all a2 equal to 0. Now, we do for, so this is, if we continued, then for a2 equal to 1, I can write again all 4 values, that means a1 equal to 0, a0 equal to 0, a1 equal to 0, a0 equal to 1, a1 equal to 1, a0 equal to 0, a1 equal to 1 and a0 equal to 1. So, since a2 equal to 1, so always I get this x square term should be always there. So, first I write for all the polynomials here I get x square. Then it is all 0 0, then here it is 0 plus 1, here it is x plus 0, here it is x plus 1. So, the 8 polynomials we got this, the 8 polynomials, that means here 2 to the power 3, where p equal to 2 and n equal to 3. The polynomials are that we got 0 1 x x plus 1. So, polynomials are 0 1 x x plus 1, then here we get x square plus 1, x square plus x and x square plus x plus 1. Now, we can also represent these polynomials by binary codes. How? See, here I have 3 terms. Since I have the polynomial is of the form a2x square, a1x and a0. Then mainly that whatever the value of a2, a1, a0, so that gives me these all these polynomials. So, if I write, say here mainly we are getting this for a2, a1, a0, where these a0, a1, a2 can take values from z2, because my p equal to 2, that means 0 and 1, that means 0 and 1. So, if I take all possible values of these, and we will see here there are 8 and we know from 0 0 0 to 1 1 1. So, if I continue that next page, if I write all possible values, that a2, a1, a0, we give the values 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So, we will give that, see 0 0 0 means the, if I write now the polynomials, so the polynomial will be here 0, as if this is my 0th term, or if I again write that x to the power 0, if the position wise we can write that as if this is my x to the power 0 term, this is x to the power 1 term and x to the power 2 term, because it is a2 x square, a1 x1 and a0 x0. So, I can write that it is 0 0 and this is 1 x to the power 0 is 1. So, this is polynomial 1. Since it is only 1, so x, so this is x, this is 1 plus x, this is x square, this is x square plus 1, this is x square plus x and this is x square plus x plus 1. So, actually the binary values, when this it is in Z2, that means it can take only 0 and 1. So, that is why this is same as that of our binary codes, and this is the binary representation of these polynomials. So, sometimes we also use this binary representation if it is in Z2, that means if my AIs are in, if AIs belongs to Z2, since it is in binary, that means Z2 is 0 and 1. So, we can there can be binary representation of polynomial. That means, if that particular term or is there a polynomial, or that particular polynomial term is there, then that coefficient is 1, that particular AI value is 1. if that particular term is not there, then the particular it is 0. Like here we take an example of x square plus 1, we take example of x square plus 1. So, x square plus 1 we can write x square, that means 1 into x square plus 0 into x, because x term is not there, and 1. So, this is actually binary representation is 1 0 1. So, binary representation is 1 0 1. Okay. So, now we have read that rules of arithmetic for the following when it is the coefficients are in Z2 or ZP. So, the coefficients of the polynomial in ZP. Now, once we get the set of polynomials, and now we can do the modular polynomial arithmetic. That means that we can divide one polynomial by another polynomial, and the remainder we will get, we can use that thing. So, what we can write, that if we multiply, if we multiply two polynomials of set S, say f x and g x, two polynomials f x and g x, that belongs to S, and we have considered the polynomial, this is the polynomial, S is the set of polynomial of degree less than equal to n minus 1. So, S consists of polynomials of degree less than or equal to n minus 1. Now, if the product becomes, or the product is such that the degree of the result polynomial, that means the product polynomial, degree of the resulting polynomial is greater than n, because if we multiply two polynomials whose degree can be n minus 1, then it can be greater than n minus 1, because I have taken f x and g x, maximum degree can be up to n minus 1. Then that will not be, this result polynomial will not be in this set S. So, the way we have done the modular arithmetic, now if we consider an irreducible polynomial, mx, which is analogous to a prime, analogous to a prime, and that is why we call prime polynomial also. We have read that definition, and we divide the product by mx, that means divide fx into gx, the product by mx, and we get the remainder Rx. See, then if I want these remainder polynomials must be in the set S. So, that means the degree of the polynomial Rx must be less than equal to n minus 1. So, I take the if Rx belongs to S, we want that all remainder, then degree of all Rx, all remainder polynomials must be less than equal to n minus 1, because we have considered the set is a set of polynomial with degree less than equal to n minus 1. So, when can I get some polynomials as the remainder whose degree will be less than equal to n minus 1? When my divisor polynomial is of degree n. That means, that is my divisor polynomial that mx must be of degree n, must be of degree n. So, now if we summarize that fx gx, again fx and gx are polynomials of degree n minus 1, less than equal to n minus 1, I should write degree less than equal to n minus 1. Mx is an irreducible polynomial irreducible means that if it has no factor, that we have read the earlier. So, mx is a irreducible polynomial of degree n. Then Rx equal to the remainder polynomial, Rx equal to fx into gx modulo mx. That means, if it is remainder, I can take modulo mx. Now, this is totally similar as of modular arithmetic, because mx is analogous to some prime number p and this is a product. So, a mod n and the remainder I can take. So, now with all this set of polynomials, because R x is of degree n less than equal to n minus 1. So, R x is belongs to S, and now that we this R x gives the if we now consider the modular polynomial arithmetic, then we will be using my all my S, the set with that all R x's, all my R x, that R x is the R x is, I can write that f x g x mod m x. So, this is the set, and with this is totally similar, and we can now we will be using this set to form the form a field. So, we started our lecture that how z p to the power n can form a field, and what we have seen, if p equal to 2 as an example, n equal to 3. So, obviously Z8, we have earlier seen that normal modular arithmetic Z8 is not a field, Z8 is not a field under for modular arithmetic, normal modular arithmetic. Now, what we have done, that we have got 8 polynomials. So, now under we will show how we have to show how z 2 to the power 3 forms a field under modular polynomial arithmetic. Since now we have 8 polynomials in the set, and in the next lecture we will continue this topic, and we will see how we can form a field under modular polynomial arithmetic.